Our next presentation is from the HDF Group and from Alexander Jelinek there. And it will be talking about the Python package for reading the ADF data description.
Yeah, all right. Well, thanks. So I'm going to talk about a Python reader for allotrope files data description. And next slide. And so the couple of things. First, I'll introduce the package, which is called H5LD. Then I'm going to show briefly how someone can use. Yeah, I've seen the comment. Yeah, about the preferences. I tried that and it clicked, but for some reason, I don't know. Anyway, coming back to my presentation, talk about briefly how to work with the data that the data description data that H5LD reads, but very briefly, and then talk again once we have H5LD, how can be utilized to read data description from ADF files in Amazon S3. And finally, and this is really optional if there is enough time, just very slowly, once the data description was read from a file, how to store it again for reuse, for example. Next slide. So about H5LD, next slide. It's a Python package, open sourced by the HDF Group. Like any other software we are doing, community issues, pull requests, code contributions are welcome. Positive criticism is welcome as well. Dependencies designed to be very simple, to the point. And so the kind of dependencies are Python 3.7 or later, H5Py and RDF lib Python packages. And I'm mentioning here the library only because for some features you would need at least 1.10.6 HDF library. Now, if you do install H5Py like most people do, you don't have to worry about that. The right library will come. But just in case that you have some system where you already have the library, but you install Python package maybe in some different ways, I wanted to mention the version number. The goal of this package is to provide independent readers for HDF5 based formats that do utilize linked data, mostly for the user created metadata. Allotrope community is one. I'm aware of another 2 communities that are doing linked data in HDF files with various ways how they approach this. And so H5LD was meant to be sort of a focal point of all these different communities and their use of HDF5 data, HDF5 format with linked data. Currently supported is Allotrope, hence this presentation. But if I have a bit more free time, I'm thinking about adding another community's approach here. And the package currently supports both command line and programmatic interfaces. So you can use it as a simple command line tool, but you can also include it in your applications. And the package is now available. This is the link to on the HDF Group's GitHub organization, and this is the link to go to the repository. Next slide. So working with ADF data description, we're using this package. Next. So as I said, command line interface. This is the example. This is how you would invoke it after installing it. This command line basically says, use the example.adf file, export its linked data as JSON in JSON LD format, and the output file would be output.json. The RDF output RDF formats are the ones that RDF lib Python package supports right now, and that basically is kernel, JSON LD, encode, and trig. There may be some others, but right now those things like the good ones to cover, and plenty of options to choose from. If for some reason there is no output file as a command line option, then the command line, executing this package will basically print out the linked data content in the chosen format to standard out. and so it can be used to ingest by another command line tool. And around here, the last command is the example how you can get the full typical command line tool usage help. Next slide. The other interface is programmatic, and that's the more interesting ones, especially for those who want to use this package in their own Python applications. I want just to emphasize the way how it is being used here in Python. The way how this with statement means that it's used as a context manager. The F variable is so-called context manager, and this is the way to allow H5LD really not to deal with how people are actually, where are the files, what are the storage backends. Really, any context manager variable, like in this case F, that is compatible with H5Py API can be supplied, and the package would work. And so in this case, I'm using obviously H5Py. I have this ADF file on my laptop. Specifically, this ADF file can be generated by running one of the first examples. And so this is the command typical template how you would use it. You use the context manager, you open your file, you supply it to the electrodf class, and then you just invoke the message that says get LD. What you get is a RDF graph object. And I just here show that in this particular case, it turns out that it has 894 RDF triples that it read from this file. Next slide. Just to show again what you get with this RDF graph object are also the namespaces. If you want to use them in other applications, again, you don't have to redeclare them yourself. Next slide. And also, the data description information actually has 3 named graphs. And so they appear in the RDF graph object as contexts. And so I'm showing here that they are still preserved. You have technical graph, you have user data graph, and you have meta graph. Next slide. So now working a little with this data description information, I wanted to use KGLab Python package. It's a fairly recent Python package, still new. It is being created with a goal to enable graph-based data science in Python. And so its goal is to be a glue between various Python frameworks for visualizing graphs, for querying graphs, for doing all kind of graph data analytics, with machine learning frameworks as well. So it's kind of a very useful thing to save you writing glue code if you want to go from one application of graph data to another. In this particular case, I'm just showing how you can use KGLab and PyVis when it comes with PyVis to visualize the nodes from the graph I read from that file that I showed you. And again, being from HDF Group, I was kind of more interested in the HDF and data cube side of RDF nodes in this graph. So I kind of colored differently the RDF nodes that are related to HDF5 or the data cube or the RDF data cube and these kind of things. But this graph on the right, if you use it in Jupyter Notebook, which is a very typical thing for Python data scientists to use, you can actually have a zoomable experience. You can zoom in, you can click on these nodes, you can click on the properties, and you can get their descriptions and IDs and labels. Next slide. Okay, so you can now run Sparkle queries with KGLab. Truth to be told, you can run Sparkle with RDFlib directly, but the KGLab gives you a nice, interesting capability that you can actually get query results as a pandas data frame object immediately. And so here I show again a very HDF-centric Sparkle query. I was interested to figure out what are the HDF groups and their members. So I ran that, and you get the output on the left side as a pandas data frame. On the right side, I show another benefit of KGLab, that you can actually visualize your query as a graph, which is a nice, interesting feature for someone to kind of get better visualization of what they want to achieve. Next slide. Yes, so this is the end of the playing with the data that you can get using H5LD. Now moving for an interesting part, how to read data description information from ADF files in Amazon S3. Again, so this is, next slide. So this is another interesting benefit from using H5LD. It opens up a number of data access options that are currently not available using Allotrop data format library. And in this particular case, you can actually go directly to ADF files in S3. And for the benchmark case, I'm using conventional way. This file that I'm going to use is on my local laptop, and I'm using it directly. The file that I'm using is actually a contribution by a community member who wanted to do some performance studies of Allotrop data format library. It only has RDF triples, nothing else in this ADF file, but it's a nice number of RDF triples. It's almost 589,000 of them. Now, I don't know if this is a little, this is too much, is it normal, typical, but I thought this is a nice number to try to benchmark various data access options. The file size itself is about 64 megabytes. So it's not large, too big, I would say, but it opens up some other options as well for data access, which I'm going to show later. In all the next cases for data access, it's always the same sequence of operations. So the HDF5 data sets that are holding RDF triple data are all read completely, everything out of them. Next, that information is decoded into RDF subject, predicate, and object information. Out of them, the package forms end-quote statements, and then those end-quote statements are fed into RDF lib for parsing, and out comes RDF lib graph object. And so for this particular case with the local file run on my laptop on an average day with average use of my laptop and all that, it takes 1 minute and 8 seconds to read all the HDF5 data. It does all these things, and out comes the RDF lib object. Next slide. So we're now moving to more interesting things. So now I move this ADF file to S3 bucket and as is, and I'm now using read-only S3 virtual file driver, which is a built option available in HDF5 library. The company does not distribute pre-built library packages with this VFD enabled. Right now, if you happen to use Conda package manager in your Python work, and specifically Conda Forge channel, the HDF5 library that comes in that channel does have this VFD enabled. If you do install H5Py with pip directly from there, from PyPy, the HDF library that comes with H5Py does not have this virtual file driver enabled. So some may use it, some may not, but I thought to show this case because it's something that currently HDF5 library does have. Truth to be told also, this virtual file driver was proof of concept written about 3 years ago after we completed a trade study for NASA about accessing HDF5 files in S3. It does not support really cloud-friendly access pattern, and because of that, its performance is really greatly influenced by the way how HDF5 file is created. And so in those most natural cases where people just move their HDF5 files into cloud object stores, it most likely is not going to work well. Because those creation properties of these files are not really meant to support good cloud access. So down here you have an example. This is how you would use it. You supply the URL. Now you have to use the full URL of your S3 object. It doesn't support the S3 URIs, which is more common these days. But H5Py does, again, you can use it directly from H5Py if the HDF5 library is built with this option. You have to provide the AWS region, your secrets to access these things or whatnot. But if all is set up, you run it, you get about 5 minutes, 4 minutes and 50 seconds. So that's definitely not good. But as I mentioned, it's because the VFD is very sensitive to how the files are created. And Next slide. The next option is actually an interesting one. So if you happen not to have HDF5 library with this S3VFD enabled, there is a Python package called fsspec that through the magic of H5Py support can actually help you get access to the ADF file. So about two and a half years ago, H5Py got this capability to use any Python file-like object as an HDF5 virtual file layer. And so fsspec provides those Python file-like objects. And also on the other side, it supports many local, remote, and embedded file systems and object stores. So with fsspec, you could basically now go to Google Cloud, to Azure, and to others, even your local. You can even have your HTTP server if it supports, just to basically have a file behind an ordinary web server. You could actually use it with fsspec. So it's very useful. And so right now, these are the commands you use. You first define that you want to use an S3 file system, so to speak. And then you have two context with statements. One is to open the object to get that Python file-like object, and then you invoke that, use H5Py with it. Again, the same usage, you get your RDF graph object, and it takes about 2 minutes and 10 seconds. And so why is the substantial difference with this approach versus the S3VFD by the library? And so I know the maintainer of this fsspec Python package, and I looked into the code, and basically what happens is that fsspec reads ahead a sizable number of bytes from the S3 object ahead of time, regardless of whether or not they will be used. And the assumption is, and this is the one that really matters in cloud data access, that getting more bytes than you ever need them, even more than you ever think you need, is much better than making small, frequent requests for data. So that's fundamentally different from the philosophies applied to file systems or conventional file systems. And so in this case, this fsspec package does get, I think, about the 10 megabytes ahead of whatever is going to be read. So if any future data happens to be in this cache, in memory cache of bytes, there is no request going back to the S3 object store, and that helps to drive down the number of requests, and therefore the execution execution time is shorter. So next slide. Now in this case is really because my ADF file was kind of of the size that this could actually work. So that's the only caution in this case. If you really have ADF files that are much bigger, they have some data that really makes them big, then this would not really apply. But in this particular case, this file is 64 megabytes, and it falls within the range where transfer speeds, typical transfer speeds from S3, can make downloading file quite economical, if you will. And so here I use, again, fsspec. I download this S3 object to my local laptop, and then I again open it as a local file and do the whole thing again. And so all these things combined comes up in 1 minute and 13 seconds. So it's only 5 seconds more time than when this file was on my laptop to begin with. So not bad at all. But as I said, if your files happen to be bigger than 200 megabytes, I think that at that point, you probably can think about other options as well. And if, of course, if your ADF file is in gigabytes, then obviously, forget about it, as they say. Next slide. Now we're moving into more involving setups. Here I'm presenting results using the HDF Group's highly scalable data service, which is sort of a middleware layer between the client, my laptop, and the S3 object store. And I'm going to talk about, in this case, ingesting the ADF file into HSDS. On ingest, in this case, I'm telling the ingest processor to actually shard this ADF file into the HDF Cloud Native format. And the benefit of this is that in this process of sharding the input ADF file, those shards are actually created that benefit cloud access. So in other words, this is the way that you can improve the access to the original ADF file in the cloud. And the most important improvement here is that the HDF dataset chunks, the atomic pieces of data that are read, are increased. And that's what I'm telling you. You know, you always go, you know, getting more data from cloud is always better than less. And in this case, when the chunks becomes bigger, the overall performance is better. And so again, in the access, I'm switching from H5Py that I used until now to H5PyD, which is another Python package provided by the HDF Group that actually works with HSDS. And so again, but as you can see from the command, it's very similar to H5Py. It's almost exactly the same command line. You only use different package. And the execution time for all this operation is 1 minute and 13 seconds, which is in this particular case exactly the same as downloading the file and using it locally. And the main reason for that is because this ADF file is all RDF triples, all data description, nothing else. And so it kind of reading RDF, data description content is kind of the same as downloading the file, because pretty much the same amount of data comes to my laptop. However, if you really have the ADF file with some other data in it, and you wanted just pieces of that other data in it, then obviously HSDS can be much, much better solution for you, because you only are able to slice the data that you want in subsequent data access. Next slide. This is an example of using HSDS, but with the original ADF file. So in this case, I did ingest the file, but I told the ingester, don't shard the file, just use it as is. In this case, as I mentioned, the dataset chunks are of the original sizes in ADF files. And so in this case, as you see, the performance is about 10 seconds worse, because now those chunks are too small for the cloud efficient access. And so the HSDS service has to work more to make all these requests for those chunks. And that, I think, is where the time difference comes. But HSDS, as I said, is the additional level of service, because you have to set up HSDS, you have to have user accounts on that and all the other things. Next slide. All right, so we are done with the accesses. I presented a number of cases that shows you different trade-offs and how much time it takes. This one, if I have enough time, because no one told me it's enough, so I assume there is enough time. So I'll continue going. In this case, this is very briefly. Now that you got your data description as RDF lib graph object, do you just throw them away when you are done with your processing, or you think about what to do and store them somehow later for reuse? And obviously, I have to say, obviously, there are much more intelligent and sophisticated ways how we can go about. I just wanted to give you two cases that I was able to play with. Next slide. And first one is that KGLab package that I mentioned earlier offers the ability to serialize RDF triples in Parquet file format. The downside of this approach is that it can only store subject, object, and predicate, and therefore the name graph part of the data description is lost. To the extent that that's important or not, I don't know, but that's how it goes. And I just used with no using some arguments, no options and anything else. I just use it as straight as is provided, offered by KGLab. And so I created a Parquet file. It took about 38 seconds to directly write to S3 this Parquet file. And when I actually tried to reload this Parquet file back into KGLab, it took quite a lot of time, almost 3 minutes. And the reason for that is because KGLab underneath uses pandas, and pandas output to Parquet. And so when it loads up the data from Parquet files, it actually gets them as pandas data frame and then goes row by row to recreate the graph object. So I think that's where it takes a lot of time to recreate the object. Next slide. And so finally, this is what I came up with. There's a lot more code, but sometimes you have to code a little bit more to get to benefit. And so what I basically said, okay, I have RDF lib graph object. Let me get the end codes statements out of this RDF lib graph object, and then since that's text, let me compress that text and save it as compressed text. And I use things that come with Python. I use the zlib Python package. Nothing fancier than that, but there are many Python Python packages that support various compression algorithms. So you could play with that and see which one compresses faster, but bigger files and all the other things, whatever you want. But this is the template how you would go about. So I basically created an object from this compressed text, and it took 35 seconds, which is not bad. And then, but when I read it back, there was a significant improvement compared to the Parquet approach, where it only took about 49 seconds. And by far, it beats reading back from the ADF file, even with a local file. So that's basically it. The next slide is just the thank you, and there are the emails, my email and the standard HDF Group's email for any kind of questions or help. And that's it. Thank you very much.